Really happy to be here. Traveled all the way from India, 24 hours of flight. I wouldn't have done this usually with the pandemic, but with Prof. Venkat's 65th birthday, I said I have to do it. So what I'm going to talk about here today is a couple of problems that I started working with Venkat when I joined Purdue, and how that has impacted my career and continues to impact my career. So that's going to be the line that I'm going to talk about today. So actually, Professor Venkat had an impact on me even before I joined Purdue. I did my bachelor's project on something on developing an expert system for vapor-liquid equilibrium equations. And I was using a shell, OPS5 shell, expert system shell, that I didn't know how it came to IIT-Madras at the time. I did my undergraduate at IIT-Madras, and then later realized that Prof. Venkat had given a talk at IIT-Madras, and he had left a CD of this program, which I started using for my bachelor's project. And it was such a pleasure to be admitted to Purdue and then work with Prof. Venkat later on. So just to give you an idea of how far ahead some of this work was, the very first problem that I got to work on at Purdue, I'm going to call it as PSC, natural language processing. So we now know you have systems that convert Japanese to French, French to Hindi, and all that. The very first problem that we looked at was if you gave a system process data, can you convert that to language? So in other words, I just have data, and the output should be English, for example. So you could take something like this, and then your system will say this variable is oscillating, and so on. The way we solved this problem, and I just wanted to come back to this later in the talk, is we broke this into primitive structures, and then we had neural networks those days. Again, it was the second wave AI in a high, so we used neural nets to identify these primitives. Then you could construct these sentences. You could use context-free and context-dependent grammar, and then convert that kind of data into explanations and so on. So this was the very first problem that I worked in 1990 when I started my PhD at Purdue. Of course, the second problem that I worked with Prof. Venkat is on fault detection and diagnosis, and this is something that I continue to work on. And in the short time I have, I'll tell you the latest things that we are doing with this now. So it's actually a real pleasure to work on a problem which you started during your PhD, and well, now 30 years later, it's still an exciting problem for you, and there are so much new things to still do. So that's an exciting thing here. So this problem, most of you know, you have a process, and Professor Warren Cedar also talked about it. You have sensor readings. Safety is about predicting whether things are going to blow up and so on. Diagnosis is about predicting whether things are going to go abnormal. Can you do something with it and all that? And you can look at multiple faults. You could have actuator faults. You could have structural faults. You could have sensor faults, and so on. Now, the next slide might look like self-promotion, but it is not. It is just to tell you the kind of impact working with Professor Venkat has had in my career. The top 4 papers that have been read from my work are all with Professor Venkat. 3 of those are the review papers, which are in the top 3 cited papers in computers and chemical engineering of the top 10 papers. And the other one, the one I showed you about this natural language processing for data, is one of the top 50 cited papers in engineering applications of artificial intelligence. So this is the kind of impact I had. So I had not looked at this data, but since I was giving this talk, I just wanted to see how many papers we have published together. Do you know how many papers we have published together? Okay. So I just did this just so that I know. So we have overall published 20 papers together, which have about 8,923 citations, about 450 citations on an average per paper, and you have the lowest and highest number of citations. So this is just numbers that I pulled out, and this has been the impact of working with Professor Venkat. Quickly, in the next 10 minutes, I'll try to wrap up in the next 10 minutes. What I want to do in this talk is, since fault detection and diagnosis is an area that I worked in, just want to look back and then see where we are right now and what are the exciting problems that are still left in fault detection and diagnosis. So by the time I finished my PhD and then we started writing these review papers, we had classified diagnostic methods as quantitative methods, qualitative methods, and process history methods. Just to give you an idea, this whole part of the graph is actually more control theoretic approaches for fault detection and diagnosis. This part of the graph you would recognize as now AI, symbolic AI kind of approaches. And this part of the graph you would now recognize as machine learning. So all of these new terms, but we had classified, looked at these in around 92 to 95 time frame, with me and people before me, particularly Surya and so on. Over the next 10 years, there are lots of advances in this, and I'm not going to belabor these points, just quickly tell you, in terms of this quantitative control theoretic approaches, there was a lot more focus on how you solve this problem for nonlinear cases. And many of the fault detection and diagnosis problems were set in deterministic setting. So how do you tackle these problems in stochastic setting? How do you characterize noise and the impact of noise on diagnostics, such as what Professor Warren Cedar talked about, and so on, and computational tractability. This was what was going on for the next 10 years in quantitative control theoretic approaches. Of course, AI was still in a trough. The qualitative approaches, there were more work on how you bring in more quantitative information into these qualitative approaches, such as order of magnitude, fault propagation times, and things like that. And in terms of database methods, was where maximum action was happening. And again, the basic idea is how would you solve these problems for nonlinear cases? We all know principal component analysis works in the linear case. So there were these kernel-based methods which were really picking up. And then there was this whole sub-area of how do you choose sensors so that you can do fault detection and diagnosis and so on. This was going on for about 10 years. And then suddenly we had this machine learning AI tsunami. 2010 onwards, wherever you go, everywhere it is AI, machine learning, and you start thinking about diagnostics as a big data problem. So when you think of diagnostics as a big data problem, what are the new things? Where are we going, right? What are things that are different from what we have had before? So the first thing is, when we looked at fault detection and diagnosis before, we were largely looking at process data. But now with the ability to collect incredible amounts of data and efficiently processing them, you could use all kinds of data in diagnostics. Now you could use audio, you could use video. You know, if there is a pop, that's data that could be stored. You could have video, fire, and other things. You could have smell, something comes out. So all of this data now is coming into diagnosis. And this is being curated. You have this big data frameworks from which you can easily retrieve data and so on. And how does one really think about this in terms of how do you leverage all of this in fault detection and diagnosis? And I'm going to give you just a few things that we are thinking about. When we looked at model-based, this control theoretic kind of approaches for diagnosis, we were actually taking data which is temperature, pressure. The models were very clear. Now, suddenly, if you have a model where you can also add these data, so the sensors corresponding to this data, how do you bring them into this framework in modeling and so on? That's a very important question. So how does one assimilate this disparate data into a diagnostic technique is a question that needs to be answered. The two most important questions that I have personally been working on, because we started working on this in a lot of industrial problems. And because of big data, you start getting tons of data now. But unfortunately, you get tons of data, but they're unlabeled, right? So when you're doing a simulation, you can do a CSTR. You can say, here is a catalyst deactivation, here is a fouling factor, and I have this fault data, and it's labeled, so I can do diagnostic techniques with those. But now imagine that, so this is a real problem that we are working on. So we're working on HVAC diagnostics with a company, and they have about 1,500 locations from which they are collecting data. These are all designs. They are basically the same HVAC process, but the designs might be different because you're cooling a small room, big room, so that would be different. And faults might be different, but you have tons of data from this 1,500 locations. Now you do diagnostics with this. So that's a question. No models, no annotation, no labeling. So how do you really look at this data? I think there is a big challenge for the diagnostic community. The AI community in vision and language processing and so on have been able to come up with models which seem to transcend applications, right? So you have these vision models that you can take from one place and apply it in another. is it possible to do that kind of transfer learning? So can you get a model from a particular location and be able to take it to another location and then do diagnostics with it? So this transfer learning idea is a very important idea that needs to be pursued. The other idea is this unsupervised labeling. So I have this data from 1,500 locations. I don't know what faults are, and the designs are different, but the basic process is the same. Is there some way in which I can leverage all of this data and then come up with a system in an unsupervised fashion? That's the next AI problem from a diagnostics viewpoint that needs to be solved. So if you ask me, in terms of the most exciting ideas that are around in fault detection and diagnosis and what we should be working on, I would say the first thing is go more towards hybrid model. So how do you integrate knowledge-based and data-based AI? In fact, a data-based AI is actually a misnomer, right? So when people initially talked about AI, it was all about models. Only now, people talk about neural nets and tons of data for building these AI models and so on. So how do you integrate these two ideas? And some of the things that we have been doing, you need really new transdisciplinary math. This math is not as if it doesn't exist anywhere. You have to figure out where to bring that from. And these are very important when you look at solving these problems in an unsupervised fashion. So I have two applications here. Given that I have 3 more minutes, I'm going to do one application quickly and then show you how some of these ideas are happening. So one of the problems that we recently are working on is, again, similar to the HVAC problem. You have tons of data from different flights, okay? And this company gave us maybe around 1,000 flight data, and then said, some of these are abnormal. I'm not going to tell you which ones. Can you figure this out? So this is completely unsupervised. So we tried many techniques. One technique that works, which is called multifractal analysis. I'll very quickly go through this. I'm not going to go into the math of this and so on. So the basic idea is when things are working normally, there are multiple elements in your fractal behavior. And as they go towards an abnormal behavior, it kind of goes to a single point. Okay? And this has been shown in multiple applications. So we're trying to see whether we can use some of this here. So again, the context is there's no labeling for the data. You just have the data, and you have to figure out what's going wrong. So just very quickly, I'll go through this. So when you have a time series data like this, you're trying to do analysis. So there is something called an Hurst exponent, which tells you what fractal scale this data is in. And after all of this math, what you'll get is this, and this is the multifractal spectrum that you get for the data. So what we had tried to do with this data was we had tried multiple techniques, and none of those techniques would actually pick out these abnormal time series data. It's not at all obvious looking at this data if you look at them as time series. So just to give you an idea, we plot all of these time series in this multifractal plot, and you'll see that some of these are abnormal. Okay? Then what we did was we said, okay, how do I completely do this in unsupervised fashion? I have all of these multifractal plots. I take a normal plot, which is the average, that is the normal behavior of this flight, and then look at the distance of all the others from that. And the distance is not a very simple distance. We did something called a Procustus analysis. I think this is the original serial killer from Greece, I think. So this is a person who cut people into different sizes so that they could fit the size of a bed. So this is your original. And that the context here is that you kind of match this data to your normal and see how well they match. And so your normal is this green, and then you have this multiple flight data, and then see which one fits well. And here you go. So we could find these abnormal, completely unsupervised fashion. And the reason why I'm presenting this here is because when we went back and showed these results, these were actually the abnormal cases, which was a very exciting development for us because this was absolutely unsupervised. I think there's a lot more that we need to do in this area, and this is where we are going. One other slide, and I'll stop, Stratos. So I have more, but coming back to this problem, recently what I have been interested in is how do you, so if you have lots of data, because we see all of this data, is there a way in which, again, in an unsupervised fashion, you can generate these knowledge hierarchies? What do we mean by knowledge hierarchies? What we mean is at the base level, there are certain primitive structures, and then they connect to certain other structures and so on. If you take an example of English, you have alphabets, you have words, you have sentences, you have paragraphs, and so on. Can you do this in any application, and it has to be application agnostic. Okay, so that is the area that we are working on, and I show this plot here because then at some point I realized if you think of this data as ones and zeros, essentially in this case where we worked with process data, we knew what the primitives were. You step back one level and then say, I don't even know what the primitives are. Is there a way in which I can identify these primitives and I can construct this multiple level of hierarchies which will explain what is happening in the process is a problem. Again, the reason why I'm mentioning this is again a very unsupervised problem. Just one last plot with very exciting result that we got recently. What we did was we took text from multiple documents, and then we didn't say these are the alphabets. So the program does not have an idea of alphabets. And then we asked, what is so the coding size, the primitive coding size could be fixed or variable. So we said, let's do a fixed coding size, and then try and identify whether we can find the coding size. And interestingly, we were able to, this plot is a lot more difficult to explain, so I'll just tell you the answer. Interestingly, we find that the primitive coding size 8, ASCII coding, 8-bit coding. And purely unsupervised, we get the alphabets, and from the text that we see how the distribution of that matches with the English language distribution of the alphabets. So the blue line is the actual English language description of the alphabets, and this is the primitive structures that we have got from our data, which we plot in terms of an histogram, and you can see how nicely it kind of matches. So this is completely unsupervised. Now you can ask crazy questions like, for example, if you have some bird song, 2 bird songs, these are all 1, 0. Does a sparrow talk to a crow? Right? So you figure out how many primitives are common and then say, maybe there is something here. But these kinds of things you can do in a completely unsupervised fashion. Anyway, all of this, the way to think about different problems and way to be really different, I think I learned a lot from Professor Venkat, and I thought I should come here and acknowledge this, and thank you very much.